Listening to a tree seems like an odd thing to do, but this tree isn't silent. Even through a stethoscope like this, I can hear creaking and groaning as the branches move in the wind. And there are other sounds in there that I can't quite hear with this, crackling, popping sounds. It happens because the tree is drawing water up from its roots to its leaves, and on a hot sunny day like this, as that water travels through the tiny tubes around the outside of the tree, bubbles form, and those are what are making the crackling noise. So, although you wouldn't know it by looking at it, that crackling noise could tell you that this tree is thirsty. Before we can unlock all the secrets of sound, we need to understand it at a fundamental level. So in this programme, I'm going to explore what sound is and how it's made. First, it would help if I could turn a sound into something we can actually see. This is a very special space. It's called a hemi-anechoic chamber. And what that means is that all the walls and the ceiling have these funny shapes on them that are absorbing sound, so it's really quiet in here. It's the perfect environment to isolate a pure sound and observe its effects. All I need is this small army of candles and a speaker. To make this work, I need the sound to be really loud, so I'm going to wear ear defenders. Really deep sound. You can see the speaker going in and out. And what you can see is that the candles are vibrating. There's very, very fast vibration. The individual candle flames are showing the movement in the air caused by the speaker. What's happening is that the speaker here is producing enormous amounts of sound by pushing on the air. And that pushes on the air next to it, which pushes on the air next to it, and it travels out across the candles. The candle flames are flickering back and forth 20 times per second, or at 20 hertz. And this is the frequency of the sound we're hearing. I'm going to turn it up. If I increase the frequency, the candle flames flicker even faster. And what you can see is that the candles are all flickering, but they're all flickering together. This is synchronized movement. They're all moving forwards and backwards together. So what we're seeing is the sound. The movement of the speaker causes the air molecules to oscillate back and forth at a specific frequency. These oscillations travel through the air as sound waves, and they're picked up by our ears. A loudspeaker is actually a very unusual way of making sound because it's artificially manufactured to generate any sound you like. Most sound is much more interesting. That's because, unlike the loudspeaker, most objects create a specific sound that's unique to them. And this is ultimately at the heart of why sound is such a rich source of information about the world. I'm going to do a modern-day version of Chladni's experiment. This is a Chladni plate. It's just a flat metal sheet that's held in the middle. And if I hit it, it makes a sound that doesn't sound very pleasant. It's certainly not nearly as nice as Big Ben. But that sound has a lot in common with the sound of Big Ben because it's made up of lots of different frequencies. And Ernst Chladni came up with a really clever way of picking apart where that sound comes from. So he started with a plate like this, and he sprinkled sand on top. So I'm going to do that. And then he set the plate vibrating. And I'm going to do that with a signal generator here that's going to move the middle of the plate up and down. And the number on the front here is the number of times every second that vibration is going to happen. So at the moment, it's 240. So if I turn this on. So it's not a pleasant noise. You can see the sand is dancing about on the plate, but it's not too exciting so far. But what happens if you turn the frequency up is quite different. And suddenly at this frequency here, it's 264 hertz, you can see this beautiful pattern pops up in the sand on the top of the plate. And what this is giving away is that the plate is vibrating in a shape, and the sand is showing us what shape that is. What's happening is that the plate is bending like this, and at the parts of the plate that are moving a lot, the sand's getting bounced away. And the parts of the plate that are between a bit that's going up and a bit that's going down don't move at all, and so the sand accumulates in those places. So what Chladni had found was a really clever trick for seeing the shape of the vibration, even though he couldn't see it with his eyes. The vibration pattern revealed by the sand occurs at what's known as a natural frequency of the metal plate. This is a specific frequency at which the plate naturally vibrates and produces sound. And this is part of what's making up the sound when I hit the plate, but it's not all of it, because if you keep turning the frequency up, there's more to see. And so here we are up at 426 hertz, and suddenly out of that mess there's another pattern of vibration, beautiful pattern on the plate here. Chladni's experiment reveals how a simple object, this metal plate, can produce a complex sound. Because it doesn't just vibrate at one frequency, it has many natural frequencies, each corresponding to a different pattern of vibration, more elaborate than the one before. When you hit the plate, what happens is that lots of those vibration patterns all happen at the same time, one on top of the other. Each one contributes their natural frequency to the mix, and that combination is what makes up the sound that you hear. Every object that vibrates has its own combination of natural frequencies, determined by its physical characteristics. And together, these frequencies form a unique acoustic signature. So there's a beautiful relationship between an object and the sound that it produces. When you hear a sound, you're hearing messages about the thing that created it, its size, its shape, what it's made from, even how the object was made.
I miss not hearing the birds. I lost my hearing very, very quickly. You can't believe it's happening. You think, oh, did I hear something? But no, you don't. It really is frightening.
This is Barbara. She lives with her husband Tony, and they've been married for 53 years.
What's funny? What's funny?
But for the past year and a half, they've not been able to communicate properly.
Crashed on the wires.
Because very suddenly, Barbara became profoundly deaf.
I can't hear anything round out here. I just miss my old life in general, really. Yeah. Not sort of hearing people or knowing what they're talking about. That's quite difficult. Deafness is a lonely world.
Barbara lost her hearing because just one small part of her ear stopped working. When sound enters a healthy ear, it gets funneled through to a coiled-up structure called the cochlea. a spiral-shaped cavity containing some 16,000 specialised cells called hair cells. As the sound wave moves through the cochlea, the cell's hair-like protrusions are displaced, causing the cell to send electrical impulses along nerve fibres that are destined for the brain. But Barbara's hair cells are no longer working, which means that although the rest of her ear is healthy, her brain is completely starved of sound.
I miss my independence. What I try not to do is get down. I try to think positive.
How are you feeling about
Okay.
today?
I'm okay, yeah.
Okay. How about you?
Yeah. Bit nervous, I suppose.
A month ago, Barbara was fitted with a cochlear implant. An array of electrodes has been threaded into her cochlea that will take over the role of her faulty hair cells. And today, at Southampton University, it will be switched on and tested for the first time.
So I'm going to switch it on, okay? Can you hear anything?
Not yet, no.
Just going to bring it up.
Nothing. Very faint. Very, very faint. Very gradual, isn't it?
Yeah. Is it a bit more?
Yes.
I'm going to keep talking as I bring it up, okay? Just going to keep bringing it up. How did you get here today,
I
Tony?
can hear, can't understand. I can almost hear my own voice again.
How's the volume now? How's the volume?
Yes.
The volume.
The volume. How's the volume now, you said? Yes?
Yeah.
What can you hear? Can you hear me?
Yes, I can
Can you?
hear you.
Oh dear.
That's good. Yeah.
For the first time in over a year, Barbara's brain is receiving sound signals.
Okay.
That's amazing. When you take it off, I can hear nothing.
Amazing, yeah.
Don't make me cry. Oh, don't worry, I won't.
So you're noticing the difference?
Incredible.
Stop it, you're going to make me cry.
Thank you. Oh, dear. I didn't think it would be this quick.
No, you're doing really
I
well.
thought for my birthday in July, I might
you?
better hear that.
What are we going to have for dinner tonight? Some champagne? Eh?
Stop it, I made me cry again.
Barbara is no longer lost in silence. By translating sound into electrical signals, the implant replicates the cochlear's key job, returning Barbara to a world full of sound